Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azwan bin Muhammad Sofyan, ID number 5521811708 And now I'm going to present about the principle of convective heat transfer. Convection is the mode of energy transfer between a solid surface and the adjacent liquid or gas that is in motion, and it involves the combined effects of conduction and fluid motion. Heat transfer through the fluid layer will be by convection when the fluid involves some motion, and by conduction when the fluid layer is motionless. The presence of bulk motion of the fluid enhances the heat transfer between the solid surface and the fluid. The faster the fluid motion, the greater the convection heat transfer. Okay, now the fluid properties of convection heat transfer, because it strongly depends on this: dynamic viscosity U, thermal conductivity K, density P, specific heat Cp, fluid velocity V, geometry and roughness of the solid surface, and the type of fluid flow, either streamline or turbulence. Conduction versus convection. For conduction, the transfer of heat by the interaction between adjacent molecules of a material, and for convection, it involves the transfer of heat by the mixing and motion of a fluid due to the density difference. These are the formula for both conduction and convection. Okay, so to explain more about convection and conduction in the picture, you can see here, the conduction is the transfer of heat or electric current from one substance to another by direct contact. Meanwhile, for convection, it is the transfer of heat through a fluid, liquid or gas caused by molecular motion. In this picture also, we can see there are conduction and convection taking places. Alright, so to explain, the transfer of heat by mixing the warmer portions of the fluid with the cooler portions. The density differences in the fluid arising from the heating process provide the buoyancy force required to move the fluid. The hot fluids are lighter than cool fluid and they tend to rise. Okay, so for conduction, we can see the heat energy from the Bunsen burner is transferred to the beaker by conduction here. Next, okay, the hot air rises. This leaves empty space at the bottom of the column of rising air. The cold air moves into the empty space and the fire warms it. The newly warm air also rises. So the air will only spin like this in here. As the warm air gets close to the ceiling, it loses some heat. Now the air is cooler. It follows the cool air which is falling. The cool air falls and then is drawn upwards again. Okay, this is the heat transfer from a hot surface to the surrounding fluid by convection and conduction. For A, the forced convection, the fluid is forced to flow over the surface and it involves external energy, for example pump, mixer and fan. For B, free convection, any fluid motion caused by natural means such as buoyancy effect, density diff. So you can see here, there's no pump, there's no mixer, or there's no fan. This is only the natural air. And for conduction, you can see the similarity of conduction and convection. Both mechanisms require the presence of a material medium, but the difference is the convection requires the presence of fluid motion. Okay, so these are the examples of conduction and convection in real life. When ironing a shirt, the iron is hot and heat is transferred to the shirt. So the warm iron will iron the shirt, and when the shirt is cool, the heat from the iron will make the shirt heated. And for the next picture, the ice cube will melt in your hand. The heat is being conducted from hand into ice cube. And for the air conditioner, cooling unit in an air conditioner is placed at the top of your room. When warm air rises up to the cooling unit, it is replaced by cold air and the room will be cooled. And lastly is the hot air balloon. The air inside balloon is continuously heated, which makes it warmer. The warm air rises and the balloon also rises. Okay, so this is the formula for the rate of convection heat transfer, and it is proportional to temperature difference. Q convection equals to H TW minus TB, and the unit is in watt per meter squared. Or H times A is area, TW minus TB, and the unit is watt. Q is the rate of heat transfer, watt. H is the convection heat transfer coefficient, watt per meter squared, degree Celsius. A is the surface area, meter squared. TW is the surface or wall temperature in degree Celsius, and TB is the field or bulk temperature in degree Celsius. These are the formula. From this you can arrange as this, where R convection is 1 over HA. So for convection heat transfer coefficient H, it can be defined as the rate of heat transfer between a solid surface and a fluid per unit surface area per unit temperature difference. The convection heat transfer coefficient H is also known as film conductance. For the calculation of heat transfer Q, the value for H has to be determined first for either in natural or forced convection, if the value of H is not given. Therefore, the value of heat transfer coefficient H must not be evaluated from the Nusselt number. The SI unit for H is watt per meter squared Kelvin, and English unit is BTU per hour feet squared Fahrenheit. The convection heat transfer coefficient H is a strong function of velocity. The higher the velocity, the higher the convection heat transfer coefficient. The fluid velocities associated with natural convection are low, typically less than 1 meter per second. Therefore, the heat transfer coefficients encountered in natural convection are much lower than those encountered in forced convection. Okay, so we are going to try this question. First, we have to read the question first. A 1.4 meter long, 0.2 cm diameter electrical wire extends across a room that is maintained at 20 degrees Celsius. Heat is generated in the wire as a result of resistant heating, and the surface temperature of the wire is measured to be 240 degrees Celsius in steady operation. Also, the voltage drop and electric current through the wire are measured to be 110 voltage and 3 ampere respectively. Disregarding any heat transfer by radiation, determine the convection heat transfer coefficient for heat transfer between the outer surface of the wire and the air in the room. So, it is important if we jot down the things that you can get in the question. So as we can see, the length is 1.4 meter, the diameter is 0.002 meter, the TW is 240 degrees Celsius, the TB is 20 degrees Celsius, TW is the wire and TB is the air. And the voltage is 110 voltage, while the current is 3 ampere. After you have jot down all the necessary data, we can use all the formula that we know. So Q, the energy generated, can use as VI. The area we can use pi d times by L, and as we all know, Q is equal to HA TW minus TB. But we want the heat transfer coefficient, so we just rearrange it and make the H as the subject. So we calculate first the Q, 110 voltage times 3 ampere equals to 330 watt, and then we calculate the area, pi d times L. Pi we move at the outside, and then the diameter 0.002 meter and the length 1.4 meter. After you have calculated, you will get the answer is 0.0088 meter squared. And as for H, we just put in all the information that we have, 330 watt over 0.008 m squared times by 240 degrees Celsius minus 20 degrees Celsius, TW minus TB, and the answer is 170.5 watt per meter squared, degrees Celsius. Lastly, I'm going to explain about lamina and turbulent flow. For lamina, it has smooth streamlines and highly ordered motion. For turbulent, the velocity fluctuations and it is highly disordered motion. And for transition is from lamina to turbulent does not occur suddenly and before it becomes fully turbulent. You can see in this figure, it shows you that the lamina has highly ordered motion while turbulent has the highly disordered motion. You can also see the laminar flow and turbulent flow in this figure. The laminar flow is the early part of the smoke coming from the cigarettes, and the turbulent flow is this, the later part of the smoke coming from the cigarettes. Okay, thank you, and my friends will later explain to you about the types of convection that we have. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Rashdan Nabil bin Ramlan. Okay, before that, we learn from Mr. Muhammad Azwan about the principle of convection of heat. So, I continue the presentation. So, in this topic, we will know the types of convection, which is two. One is free or natural convection physical process, and next is forced convection process. Okay, do we start? What is the free or natural convection physical mechanism process? It is the process where any fluid motion occurs by natural means such as buoyancy, and it is often not noticeable because of the low velocities involved by the nature. Okay, let's take some examples. So here we see a can of cold soda, and there is warm water surrounding the cold soda. So the warming up of a cold drink in a warmer environment by natural convection is one of the example. As we see warm air surrounding around the cold soda tin, and the heat transfer from the soda to the outside, and that is one example. So this is another example. We use chicken egg. So we can see the hot egg begin to cold because due to the surrounding there is cool air moving around the hot egg, and the heat in the hot egg begin to go out. As we know that heat move from high temperature to low temperature, and as soon as the hot egg is exposed to the cool air, so we see the expression, the T, which is the temperature of the outer surface of the egg shell, will drop, as I say before that, and the temperature of the air adjacent to the shell will rise as a result of heat conduction from the shell to the air. So the egg will soon be surrounded by a thin layer of warmer air, and heat will then be transferred from this warmer layer to the outer layer of air. Next, the cooling process in this case would be rather slow, because since the egg would always be blanketed by warm air, and it would have no direct contact with the cooler air farther away, and the temperature of the air adjacent to the egg is higher, thus its density is lower. Since at constant pressure, the density of a gas is inversely proportional to its temperature. And lastly, low density or light gas is surrounded by a high density or heavy gas, and the natural laws dictate the light gas rise. The space vacated by the warmer air in the vicinity of the egg is replaced by the cooler air nearby, and the presence of cooler air in the vicinity of the egg speeds up the cooling process. The rise of warmer air and the flow of cooler air into its place continues until the egg is cooled to the temperature of the surrounding air. This will mean that initially this egg it is very hot, and due to the cold air surrounding, the process will occur the heat transfer from the inside of the egg to the outside of surrounding until the temperature of the egg is same to the temperature of the air surrounding it. Okay, next one is the heating of cooler room by heat convection. This is one of the principle of the natural heat convection. We can see that in the room production, in the room, there will be different temperature, high and low temperature. As we can see, the temperature are moving around this room. We can take example from mainly in the house at the New York. They use exhaust to take out the cold from their houses by putting some sources here like wooden. They burn it, so their house is not fully cool. And we can see the explanation. The less dense fluid rises because of its relatively high buoyancy. So gas will move upside or down due to its buoyancy, and fluid is moving not by force. So next one is Grashof number or GR, and we can see the equation here. We use this expression to interpret physically as a dimensionless number that represents the ratio of buoyancy forces to the viscous forces acting on the fluid. And we can know that the Grashof number in natural convection plays a role similar to the Reynolds number or RE in forced convection, which is can be explained later. So we take a look at this formula, how to complete this equation by inserting this G, which is gravitational acceleration, which is 9.81 meter per second square, and beta like alphabet, which is represent volume to a coefficient of expansion of the fluid in 1 over Kelvin. So how to get B? We can use this. So the LC we can include in the slide later, and the U from the formula is kinematic viscosity of the fluid. And the next one is the Prandtl number of dr, which is describe the relative thickness of the velocity and the thermal boundary layer. Next one is Nusselt number. Nusselt number is the combination of coefficient, exponent, and Rayleigh number. And in natural convection, HT correlations are usually expressed in terms of Rayleigh number raised to a constant n, which is multiplied by another constant c. We can see this, both of which are determined experimentally. And this Nusselt number is common practice to find out the heat transfer coefficient of H, which it shows the result of convection relative to conduction. And it means if the higher the Nusselt number, the more the effectivity of the convection heat. So convection force on heat can be applied to many situations. And the first is for vertical plate and vertical cylinder. This is how we can find the Nusselt number, which is using this equation, and the range of the RA is entire range. We can take note this as it is vertical plate or cylinder. we can assume that its LC is equal to L, which is the length of the plate. Okay, for the isothermal vertical surface of plate, the free convection heat transfer coefficient can be expressed by the following general equation. We can use the earlier or this one. Next one is for the horizontal. We can use this. We cannot confuse the usage of the vertical and then horizontal cylinder because it is a little bit different. From earlier, we see from the vertical plate that is LC equals to L, but this horizontal cylinder, its LC is equal to D, which is its diameter. Also, same to the sphere. Okay, take a look at the type of geometry and the characteristics line, which is LC. It is a little bit different, and it is also have a different range given, and also different type of how to find the Nusselt's number. So that's all from me, and we proceed to the next presenter which is Muhammad Zuhairi. Thank you.
Ismu Ahmad Zuhairi bin Osman Sani. What is the meaning of post-convection? Post-convection is the special type of heat transfer in which fluids are forced to move. There are external post-convection and internal post-convection. External post There are three types of the external post-convection, such as parallel overflow platelet, cross flow over cylinder and sphere, flow across tube bank, and internal post-convection, laminar transition and turbulent flow in the tube. There are examples of the post-convection. Heating a room by means of fan post heater. To cool the room, we use a anti-clockwise fan to mix warm air. Post breeze air create downward. And for the winter, the fan should rotate clockwise to pull cool air up from volume and push warm air downward curve upward. And secondly, mechanical agitation greatly increase the motion of the fluid. Post convection, velocity ingredient less T1 minus T2. When the fluid is in turbulent flow, the temperature is small. Here, the example is through convection. For T5 to T6 similar to T1 to T2. Velocity gradient step T2 until T3 in the thin basis sublayer when there is no turbulence. Its transfer is mainly through conduction. For T4 until T5 similar to T2 until T3. The velocity profile in this boundary layer is unlike the velocity profile in free convection boundary layer. In post-convection, another dimensions are used to collect data for H, which is R, RE, and PR. RE is meaning Reynolds number. PR is Prandtl number. And the other unit is Nusselt number, NU and MA mass number. That's all for me. Thank you.
Hai, Assalamualaikum. 5 subcomplete 5.3, that is dimensionless number. Okay. The first one is the Nusselt number, NU, represent the enhancement of heat transfer through a fluid layer as a result of convection relative to conduction across the same fluid layer. The heat flux through the fluid layer by convection and by convection can be expressed as respectively. Okay. The formula is Q convection over Q conduction is equals to H delta T over K delta T divided by L. And it is also can be calculated by HL over K, and is equals to NU. Taking their ratio, Q convection is equals to H delta T, and also Q convection is equals to K times delta T over L. NU is equals to 1 Q convection. There are two types of convection. The first one is free convection, and the second one is forced convection. Free convection is divided into 4 things. The first one is Rayleigh number, RA. The second one is Grashof number, GR. Third one is Prandtl number, PR. And the fourth one is Nusselt number, NU. And the second, forced convection. The forced convection is divided into 3. The first one is Reynolds number, RE. The second one is Nusselt number, and the third one is Prandtl number. This is the Reynolds number. Reynolds number equation is RE. The RE equation is RE is equals to inertial force over viscous, and the formula is Z over viscous to V, and it's also equals to here density times V times LT over mu. Okay, the mu is the dynamic viscosity, and the LT is the characteristic length of the geometry in meter unit, and the P is to find the V, we have to do mu over density, and it's the name of the V is kinematic viscosity, and M2 over S. Next slide. And next, we will see the forced convection. NU will also be used in order to determine the value of H. General equation of determining H is equals to this one. NU is equals to Hx over K. And it's also equals to C times Reynolds number, the power of M, and Prandtl number, the power of 1 over 3. C and M here, where is C, that we can find at table 4.1. Equation is divided into this. So I will try to explain about the first one is for the flat plate. The flat plate is divided into 2. The first one is laminar flow, and the second one is turbulent flow. Okay, if the Reynolds number, when we calculate it, is less than 5 times 10 power of 5, it will be laminar flow. And if the Reynolds number is more than 5 times 10 power of 5, it will be turbulent flow. Okay. Okay, for the laminar flow equation, we use and also Nusselt number. Nusselt number is equals to HL over K. K is the thermal conductivity, and the formula is equals to 0.664 times Reynolds number to the power of 0.5 times Prandtl number to the power of 1 over 3. And then for the turbulent flow formula, also use the Nusselt number is equals to HL over K, and also can be calculated by 0.0366 times Reynolds number or 0.8 times Prandtl number power of 1 over 3. Next time.
Yeah.
Okay, next I will be explaining about the cylinder. For cylinder with the axis is perpendicular to the flow, the equation used to predict H is, so this is the equation find the pH for the cylinder, and also you can also use this formula to find the pH also. Both are for the cylinder. Okay, where the value of C and M is given at table 7.1.
I'm Wanaina and I will continue for the part sphere. When a sphere is heated or cooled by a fluid flowing past it, we can determine the value of H by the equation of sphere. So from this is the equation when we have to find the Nusselt number for sphere. So this is for Nusselt equation, 2.0 plus 0.4 Reynolds number half plus 0.06 Reynolds number 2/3 close bracket PR value 0.4 and open bracket for mu infinity over mu surface and close the bracket 1/4. This is basically for the Nusselt number equation for sphere.
And this is the explanation for the flow across tube bank, which is arrangement of the tubes in line and staggered tube banks. A1, AT and AD are flow areas at indicated location, and L is the length of tubes. For flow across tube banks, we have some formula to find the velocity maximum in line and velocity maximum for staggered. And lastly, we have the Reynolds number for flow across tube banks. Reynolds number equal to J times Vmax times Vd over mu equal to Vmax times D over V. That's all.
Hi everyone, my name is Saida. Now I will proceed to explain about the flow across tube banks. The several correlations based on experimental data has been proposed for the average Nusselt number for cross flow over tube banks. Is equal to H times D divided by K. H is heat transfer convective coefficient times diameter divided by K thermal conductivity of the fluid equal to C times RE to the power of M PR to the power of N open bracket PR over PRS close bracket to the power of 0.25. RE is Reynolds number while PR is Prandtl number. The C, M and N is the constant where the value depends on the value of Reynolds number. All properties except PRS, which is Prandtl surface, are to be evaluated at the aromatic mean temperature. Aromatic mean temperature can be calculated using Ti plus Te divided by 2. The Ti and Te are the fluid temperature at the inlet and the exit of the tube bank. It can be seen here the value in this diagram. The average Nusselt number relations are for tube banks with more than 16 rows. This table can be seen at table 7.2. Nusselt number correlation for cross flow over tube banks for N more than 16 and 0.7 less than PR. The average Nusselt number correlation are for tube banks with more than 16 rows. This value can be calculated and can be seen at table 7.2. All properties except Prandtl surface are to be evaluated at the aromatic mean of the inlet and outlet temperature of the fluid. Average Nusselt number relation are for tube banks with less than 16 rows can be used using this equation where Nusselt number is equal to F times Nusselt number, where F is correction factor whose value are given in table 7.3. For Reynolds number more than 1000, the correction factor is independent on Reynolds number. Difference for internal flow. The proper temperature difference for internal flow, which is flow over tube banks, is still internal flow through the shell, is the logarithmic mean temperature. Logarithmic mean temperature difference can be defined as temperature difference for internal flow, which is flow over tube banks, is still internal flow through the shell, is the logarithmic mean temperature difference, which can be seen using this equation. Exit temperature of the fluid TE can be determined from this equation. And finally, the heat transfer rate can be determined from the all equation above using this equation.
My name is and now I will explain about the next topic, which is film and overall heat transfer coefficient. For this topic, the objective is to apply the concept of combination of heat transfer, which is conduction and convection in problem solving, and next we will determine the overall heat transfer coefficient U and how to use the formula. In heat transfer process, main heat transfer process is combination of conduction and convection. For example, in heat exchanger there are two H, which is the convective heat transfer coefficient for the fluid film inside the tube and outside the tube, which is 2H. And in the heat exchanger also, the thermal conductivity and the thickness also will be counted, and that's why we will use U. The first U is for U for a plate, which we can see here. U for plate we will relate to rate of heat transfer, where rate of heat transfer, which is Q, we will relate to the cross sectional area for heat transfer, which is A, and the overall heat transfer coefficient, which is U, which can be seen in the formula here. To get this formula, we must derive for U formula, which will be explained later. Yes.
Hello and hi everyone. So my name is and I will explain about coefficient of heat transfer for tube or cylinder. So in tube or cylinder, there is two type of mode of heat transfer, which is convection and conduction. So based on this diagram, we have two conditions, which is inside the tube and outside the tube. So inside the tube, the heat transfer by convection occurs between T1 and T2. And we have two conditions, which is inside the tube and outside the tube. So inside the tube, where T1 and T2, the heat transfer occurs by convection, and between T2 and T3, the type of heat transfer is conduction. So when T3 and T4, which is outside the tube, the heat transfer occurs by convection. We have three processes, which is two convection and one conduction. So each has associated with heat transfer coefficient, which is cross sectional area for heat transfer and temperature difference. This slide is basically explaining how to derive to get this last equation. So the first equation is Q is equal to temperature over resistance, which is this is for resistance for convection, and this for conduction, and this for convection. So when we derive, we get heat loss is equal to delta T over resistance total. So it is equal to heat loss coefficient U is equal to 1 over are total. So when we derive that, we will get Q is equal to heat transfer coefficient times surface area times delta T overall.
Okay, for now, subtopic 5 for chapter 5, which is critical insulation thickness. Okay, the thermal insulation are materials or combination of material that provide resistance to heat flow. So, most commonly, kita akan guna heterogeneous material yang ada low K. K itu thermal conductivity, and it will involve the air pockets. Air pockets ni dia ada lowest thermal conductivity and readily available. For example, we will use styrofoam as a packaging materials for TVS, VCRS and computers. Okay, contoh macam ni kan, heat dia boleh transfer to this area, tapi bila kita letak insulation, heat akan reflect, so heat loss yang berlaku tu akan kurang. Okay. As we know, with the temperature difference, the driving force for heat flow, and the greater the temperature difference, the larger the rate of heat transfer. Macam lagi besar difference dalam temperature tu, kita punya heat transfer akan jadi lagi besar. So, untuk kita slow down the heat flow, kita akan letak dua different medium with different temperature, which is barriers on the path of the heat flow. Untuk thermal insulation serve, such as barrier, they play a major role in the design and manufacture of all energy efficient devices or system. The thicker the insulation, the lower the heat transfer rate. So, in between the insulator tu kan heat transfer dari sini. So, bila kita ada insulation dekat sini, energy reflect and the heat loss will be reduced. Okay, for factory, heat generated in furnaces by burning coal. So, the insulations will reduce the amount of heat loss. Contoh dekat luar negara kan sejuk, so untuk kita minimize the heat loss from our body, kita akan wear either thick cloth or sweater or even coat. So the coat or sweater will act as the insulator, so heat loss from the body will reduce. For refrigerator, the insulation layers in the wall of the refrigerator itself will reduce the amount of heat flow into refrigerator. So untuk kekalkan kesejukan dekat dalam refrigerator tu, ada insulation dekat walls of the refrigerator so that the heat transfer will be reduced. Okay, the R value of insulation. The effectiveness of insulation is given by R value. So, kalau thermal resistance of the material per unit surface area is the definition of the R value itself lah. So, kita ada dua untuk R value insulation, for flat insulator and for pipe insulator. Kalau for flat insulator, formula given is R is equal to L over K, which is thickness over the thermal conductivity, and for the pipe insulator, R is equal to small r 2 divided by K, which is thermal conductivity, ln R2 over R1. Okay, once the R is available, the heat transfer rate through insulator can be determined. So, untuk kita cari heat transfer based on R yang kita ada tadi, the formula given is Q is equal to delta T over R minus V times the area. So delta T is difference in temperature, R yang kita dah cari tadi, and then we will time it with area. In the US, R value is referred as unit. An example, R20 insulation, but actually have the unit H feet square, F So for SI unit, the unit is meter square Celsius over W. Okay, for the conversion, 1 meter squared Celsius over W is equal to 5.678 H feet to the power of 2 F over BTU.
So I will present about optimum thickness of insulation corresponds to a minimum combined cost of insulation and heat loss. So this graph is cost per year versus insulation thickness. So from the graph, it contains 3 lines, which is for first curve is total cost. For the second curve, it is refer for loss heat cost. So for this linear line, it represents insulation cost. So to obtain minimum total cost, from optimum thickness and total cost, we can obtain minimum total cost. On the basis of minimum total cost, we can determine the optimum thickness. So this is the example question for critical insulation thickness. So from the question, temperature is given, which is 120 degrees Celsius. So for thermal conductivity also given, which is 15, and for diameter is 1.6. So the diameter is 1.6 cm and thickness is 0.2 cm. And so proceeds to the solution. So this is the figure of the insulation, which is cylinder. The diameter is given, which is 1.6 cm. So from the diameter we can obtain 0.8. We can obtain radius, which is divided by 2. So we get 0.8 cm. So this is R1. Kalau R2, dia dari sini ke thickness ni hingga ke wall of the insulation. The wall of insulation is have been mentioned in the question, which is 0.2 cm. So untuk dapatkan R2, tambah 0.8 dengan 0.2, which is 1.0 cm. So kita nak cari R3. So kita assume L equal to 1 meter. So by using formula of area cylinder, which is 2 pi RL, so by substituting the R and L, we can get 0.0503 meter square. So for A3, we want to find R3. To obtain R3, we use thermal resistance, which the formula is thickness over thermal conductivity for flat. While for pipe, this is the formula, ln R2 over R1 over 2 pi KL. So by substituting the value, we get answer. R total is Ri plus R1 plus R2 plus RO, which is Ri is for flat, R1 is for pipe, R2 is for pipe also, and R0 is for flat. So we substitute and get the answer. So the formula for heat loss is Q equal to Ti minus To over R total. So Ti F given in the question, which is 120 minus To, which is 25. So our total, we just substitute from this and we substitute it into the formula. So we will get R3, which is 0.017 meter.
So the question asks the fiberglass insulation thickness, which is between this one and this. So the R3 and R2. So we will obtain the fiberglass insulation thickness, which is 0.007 meter. That's all. Thank you.